Today I will talk to you not only about the spatial econometrics, which I don't know if you have background in it, but I will show you how to use these methods in your own research so that you can change the categorical data, which sometimes is troublesome, to more general matrix approach. So, as I don't know your background, we'll talk briefly about the spatial econometrics. So I will show you how this is connected to the basic linear regression and what are we using to make this research more spatial wise. Yeah. And then we will talk about user-built matrices. So this will be matrices that are used in the spatial econometrics, but based on your own data. And then we will test this theoretical solution on the toy dataset and then on the original dataset from Office of Statistics in Poland. Linear regression is the basic approach that we can use if we want to see the relation in our data in more proper form, not only x, y points, but this linear line that shows us what is the relation in our dataset. So basically, we are trying to fit a line using some variables that will explain us the relation of y. Here, if we have this categorical data, which is a problem in this case somehow, we try to omit this by encoding our data to levels or using the dummy variables that will show us how this change in category influences our result. Spatial econometric models are based on this linear concept, but here we are using this Wmatrix, which I believe you can see in 3 places in here. This is the basic model which allows us for many combinations. So we can use this Wmatrix in all those 3 places or use any combinations of them. Basically, we are just using one Wmatrix because, as you know, as many variables as far as we can get, we can only go to the overbias if it's not proper for our data set. This Wmatrix is a concept which allows us to see the neighboring pattern for our dataset. I will talk to you about that right now. So here we have our space in which we have 5 districts. And to explain to you how this Wmatrix works is as simple as that. So let's see the district number 2. This is represented in the 2nd row and 2nd column as the matrix is symmetric. And if we have the neighbor of this district 2, we just put 1. So here we will assume that a neighbor is a district that have common border with ourselves. So at each intercept of 1st and 2nd element in the matrix, so which symmetrically, and on 2nd and 3rd, we see this 1. Then we can, of course, weight this matrix, and then we can have the mean weighted by our neighboring conditions. So this matrix is very simple. The only tricky part is how we can assume what is the neighbor. So we have many approaches. We can use this common border. This is the contingency matrix. We can assume that our neighbors are those who are the closest to us or are in the specific radius. And there are many, many more. So I thought, how about using these similarities in the data as the neighbors? So we move a little bit further from this spatial approach to real data problems that we have in non-spatial aspects. So if we have this category, we can assume that every item that is in the same category is a neighbor somehow. So as you can see, as this Wmatrix is a very simple concept, we can basically just use some loops and put it in here. And then using these models for spatial econometrics, we can also make use of that matrix. So let's play with this iris dataset. I think that all the R users know it. I don't know how about the Python ones. It's basically a dataset about flowers, which we have 3 species in it. And we will train basic linear model with this categorical variable to explain one of those values. And also, the third approach will be to use this spatial econometrics-wise models. So here we are building the Wmatrix based on the species variable. So for each species, we build a variable that we put then in the matrix. Matrix is binary. Then we standardize it by rows. And then convert in this last line to a type that is recognized by spatial econometrics packages. And the most important part is the performance of our models. So as we can see, this linear with levels are basically very similar. The Bayesian criteria also tells us that the second model is no point in giving the level variable because it's only the overfitment. And then this Wmatrix, as you can see, is giving drastically better results. So the information criteria are significantly lower. So this is only a toy example, but it shows you how we can utilize the similarities in sample to produce better model. So for a real data set, this is the data set on the powiat level, spatial coded. And here we will explain the number of births in each powiat in regard to Becker's theory of fertility. So we have a few variables, which is marriages, women with higher education, and so on. And we can fit a standard linear model. And then we will build 3 different models. This second A is a model with spatial dependencies, where we put the Wmatrix lagging the dependent variable in each sample. So we look not only on the characteristic of each powiat, but also we think about how it is similar to its neighbors. The 2B is very similar to the 2A one, but the Wmatrix is different. So here we don't use this spatial basic of neighbors, but here we assume that neighbors are those similar values. So not only Warsaw and Minsk Mazowiecki similar, but Warsaw and maybe Krakow, because they are similar in terms of their general characteristic, not on the spatial point. So here I used, as a basic for Wmatrix, the similar values for birth. It's only grouping. And the first model, I used clustering results. So this is only like to show you that we can build similarities basing on anything basically you want. So it's the grouping or clustering or other method of recognizing similarities. So let's see at the performance. So the basic model, of course, is the lowest performing one because we only have the linear assumptions. And the second model with clustering in error, it's slightly better, but it's not drastically better. Second A, which is a basic spatial model, which I will do regarding of this new method, it's better because those data is has a bit of heteroscedasticity problem. So the spatial approach allows us to omit that, and this second B model is overdoing that. So we have the lowest values of information criteria. So to conclude, as it is only work in progress and to inspire you, we can see that using very simple methods that are available in SPD package, we can build our own Wmatrices and use them in any data that you want, not only on the spatial one. We can do that so that we will omit the overbias and get better results. And as we are all now in the world when we try to focus more on the white box model, because somebody tries to force us to explain it very, very carefully, so this is the way that you can improve. Yeah, thank you.